I'm a chief architect for our quantum team, and a lot of people don't know Microsoft has a quantum team or an effort going on. It's actually been going on for a long time. I'll give you some background on it and how it affects or how it interfaces to languages. And this is going to be language specific. We have a lot of other talks we give on the physics, we give on the math, we give on the theory behind it. This is mostly on the interface to our simulation system, which is called LIQUi, Language Integrated Quantum Operations. Give you an idea of how it looks, how you use it, and also a little background in what is quantum, where is it coming. We say lang.next. Well, this is a little beyond the next. We'll do a plus beyond of where things are going. But there's actually quite a bit that we can actually show today, and things are coming, some things sooner than you might expect. There's been a lot of media hype lately, and this has become an area I'm talking about more and more because people are saying, well, what is Google doing, and what are D-Wave doing, and what's NASA doing with it, and Lockheed Martin, and everybody else. And I'd like to break apart a little bit the facts from the hype and show what is reasonable, what are things you might actually do, and what's practical along the way. There are a lot of different technologies. One of the problems with quantum is anything at the quantum scale can be used potentially for quantum computing. It can store ones and zeros, and we can do a lot more than that with them. These are a few of the more popular technologies. I'm not going to go into them in this talk, but for characteristics, ion traps in the dozen range. We can build qubits, we can compute with them, we can do experiments, but they're very slow. Superconducting qubits, best example of something on the market would be the D-Wave machine, which I'll talk about a little later, using flux quanta as the unit of computation. Linear optics, really nice because it runs at room temperature, very stable, long coherence times, but you need an optical bench to do one qubit. And so the scalability is not very good at the moment. There are people going to integrated optics, but that's also something that's going to take a while to scale down and can't go to some of the other levels. Nitrogen vacancy centers, this is the stuff you hear about in diamond. Turns out diamonds aren't perfect, and in certain places where there should be carbon atoms, there are nitrogen. And where those vacancies are, you can actually do computing. Very stable, again, room temperature, but now you have to hunt up diamonds that happen to have things in them you can use and do computation with. And it's, again, not a very scalable technique, at least today. Quantum dots is another example that's analogous to the superconducting qubits, but here using charge instead of flux as your basic unit. And topological quantum computing, I'm not going to talk about at all today, but that's actually what we do. This is why Microsoft is in this at all. Is one of the main problems you'll see along the way here is errors. Noise is your enemy. And there's a way or a state of matter that you can use that is actually fairly immune to noise, almost completely immune. And it has to do with theories of topology that can be brought about in physics. So we're not going to talk too much about it. I'll mention it along the way, but this is actually the reason Microsoft is the forerunner in that area. We're the people who are sponsoring all the work in the world in topological quantum computing, or most of it at least. So what's the killer app? Everybody cares about why do you want this? And the one everyone hears is cryptography. We're going to break RSA. We're going to break all the cryptographic systems. No, that's not what's going to happen. Is there an algorithm that shows you can do the moral equivalent of breaking RSA with a quantum computer and do it in a reasonable length of time? The answer is yes. Will you ever do it? No. And the reason no is you change the cryptography. There are lots of things you can do that are immune to quantum computers just as they're immune to classical computers. So you're not going to use it to break new cryptographic codes. Old ones, possibly. There are reasons why you might want to pull something out of an archive and you have no key anymore for it. On the other hand, secure transmission of information, quantum encryption, things like that are extremely viable. We're already using fiber optics. I can quantumly encrypt the information, send it over the fiber optics, and if anyone tries to read it, it destroys itself. You have to have the right key, and you only get to read it once. And any attempt to play with it shows the tampering. So there are all sorts of areas in the area of cryptography that are interesting, but the actual breaking of keys by themselves practically is not going to be a problem. Quantum simulation, This is where Feynman started with quantum computing, is simulating quantum systems. What's better to simulate a quantum system with than another quantum system? So areas like materials design. I want to build a high-temperature superconductor, and I want to be able to predict exactly how it's going to work through simulation. I want to model chemical systems. We can talk a little about that later. This is an area that has exponential speedups over classical, things you just can never do and will never be able to do classically that you can do on a quantum machine. And we'll show some examples. And machine learning. Clustering, PCA, regression, classification, there are all sorts of areas. However, you don't get an exponential speedup. You get a polynomial speedup. In many cases, though, that's interesting. Places where we can actually get significant speedups over the equivalent classical techniques are useful. And I'll mention that a little bit in the talk as well. So let's start with the basics. We're using buzzwords, so let's actually get down to what do we really have. Everybody knows and loves bits. We have a 0, we have a 1. Everybody's happy. A qubit is a superposition of a 0 and a 1. What it means, it's some combination of information about the 0 and about the 1. It's not just it's somewhere between 0 and 1. That would be probabilistic. This actually is a 4-sphere that we're sitting on. Excuse me, 3-sphere, which is in 4 space. My mathematician friends would kill me. But there are 4 values, 2 complex numbers, alpha and beta, the magnitudes of which they're squares, sum to 1. So you're sitting on the surface of this sphere. Somewhere you're pointing on that sphere. Well, you've got 4 floating point numbers representing the equivalent of a bit. You've got a lot of information. And there's a heck of a lot you can do with that. We're going to arbitrarily define the z-coordinate as our computational basis. So north is 0, south is 1. It's just a definition. When you read out a qubit, when you look at it physically and say, what are you? You're only going to get a 0 or 1. So you can't get the richness of that sphere back out. You can compute with it. You can set it up. You can do lots of work with it. But at the very end of the day, all you get back is a 0 or a 1. And that's a major limitation. I'm going to show you where that comes up. But the 0 or 1 you get back is based on how close that vector is pointing on the sphere. And so now you get some feel of where are we on the 0 or the 1. If I ask or run the computation multiple times, I can build up a probability of where that vector is. If you're exactly on the equator, you've got a 50-50 probability of reading things back as a 0 or a 1. So that's a bit and a qubit. On the classical side, we have logical operations. You put an input in, you do the operation, you get the output back out. We have the equivalent thing in the quantum world, which is called a unitary operation. It's just a matrix multiply. Because now it's not just a bit. We have this complex alpha and beta, and we're going to multiply it by a 2-by-2 matrix, and we can move them any way we want. In this case, the alpha and beta became a beta and an alpha. And so this was a NOT gate. The difference you'll notice is there is no input or output. You can run it either way. It's a matrix. You could invert it and flip it the other direction. So you have a whole different way of looking at what you're doing. In the case of classical, it's a truth table. Every single gate we do can be described by a truth table. In this case, we already have the matrix. And so if we have something that looks like this takes 2 qubits. Qubits are going along the top and the bottom. And this is the symbol for a controlled NOT gate. If the top qubit happened to be a 0, bottom qubit goes along unchanged. The top qubit happens to be a 1, it flips the bottom. This is the NOT that we saw earlier. Sitting in the bottom, this is the control. The difference is it's not just 0 or 1. It could be any combination of those alpha, beta, gamma, and delta for 4 of them, and they all come out computing all possibilities at the same time, instead of just flipping the bit. So the fact that these two are now have gone through computation together, they are now entangled. They're now in a much bigger space. And if you're a mathematician or physicist, this is a Hilbert space we're describing. So this goes up as powers of 2 every time we add another qubit into this. And every time they come together, they become fully entangled. So again, in the classical case, everything goes left to right, input to output. In the quantum case, almost everything is reversible. You can run the whole system, your whole computation forward to the end, and then run it all the way back and get all of your inputs back. On an engineering point of view, this is actually really interesting because it's fully information preserving, energy preserving, being reversal, takes no power. So for example, I have logic gates that I run that are classical logic gates but done in this style down in the bottom of a fridge, and each gate operation is 1 attojoule of power. So we can also talk about building giant classical machines out of this type of technology, as well as quantum machines, where it's very, very low power and very, very fast. So you can see now where there's more and more interesting areas here that come along. All the time, you have a variable, you copy it, you use it for multiple things, you keep temp copies. That's how we do our software, more times than not. This is the big limitation in quantum. It's impossible to make an independent copy. You can make a copy. That CNOT gate, if you think about it, put a 0 in on one of them and information on the other, I can get 2 copies out, because you'll flip them or not and make them look the same. But now they're linked. I do anything to one of them, I've done it to the other one. They're not independent. So you have a problem. Anything you work on, you can't just save storage. You have to reload all your data every time you want to use it and get one piece of information back. Noise. We have error correction on all our chips. We know how to handle noise, know how to design for it. Quantum, it's very difficult to overcome. Noise means something in the universe interacted with my qubit. That's noise, a particle. This is Schrodinger's cat. The observation doesn't mean a human looked at it. It means anything in the universe interacted with it. So this is why we run at extremely cold temperatures. Temperature equals noise. The more temperature, the more particles floating around. So we cool everything way down. These are called fridges. I don't know why they're called freezers. I'm not the physicist involved, but they're called fridges. And we operate typically at the 10 to 15 millikelvin range is where most of this is operating. Microsoft happens to own almost, I won't say more, we own a lot of fridges. We'll just leave it at that. We're distributed all over the world that go to that range. So we need sophisticated quantum error correction, I should have mentioned on the end, and I'll talk about that a little bit. And then here's where things get more interesting. If I have a 32-bit number, I've got a value from 0 to 2 billion that I can store in those 32 bits. Quantum case, I can hold 2 billion numbers in those 32 qubits. And this is where all the parallelism, all the speed up, all the work comes from, because when I operate on those, I get the same effect. Input-output, classical is linear. You load stuff off a disk, or you load it in from memory, you put it back, you have to stream it in and out. No breakthroughs here. Same thing quantumly. I have to get the data into the machine, I have to get the data out of the machine. However, on the computation side, as you saw from how we store the data, we know in ALU I take 1 or 2 numbers in, I do something, I get the 1 number back out typically. At one time when I do an operation, I do an add operation on 2 sets of qubit registers, I get a register out that is 2 to the n adds, based on the 2 to the n numbers that came in represented by those qubits. This is the massive speed up that you get. So they're good things and they're bad things. We've been working on this, as I said, a long time. Station Q, group in Santa Barbara, is made up of theoretical physicists and mathematicians, headed by Michael Friedman, who's a Fields medalist in mathematical topology. By the way, Michael is the only Fields medalist working in industry. Quark, which is the team in Redmond, quantum architectures and computation. This group worries about the top level, the algorithms. What are you going to use a quantum computer for? How are you going to design it? What's the architecture, the engineering laid on top? The team at Santa Barbara is working about the theory behind it, and then the experimentalists actually building the experiments to see what we can make today, where we can build it for tomorrow. And finally, my team is infrastructure. I know that's kind of the death word for anything in the industry, but I head the infrastructure team, and proud of it. We do design and simulation tools. Along with our hardware partners in experimental physics, we work with some partners on the classical side. And the talk today is about LIQUi, which is the simulation system we've built that's a compilation platform. It does hardware design. It does simulation of quantum systems. It is the largest, most sophisticated quantum simulator in the world today. And I'll show you some of the results of what it's able to do. So what is it? As a simulator, we need a high enough language that's easy to implement large quantum algorithms. No one's really done this before. No one's made it so you could write really big systems and simulate them. Of course, we have classical computers to simulate on, so we have limits. There's only so far we can go, because otherwise we wouldn't need a quantum computer. So how far can we go? We want to be able to abstract what you've written. You want to be able to visualize it, automatic rendering, drawing, interaction with the system. And it should be a platform. This is Microsoft, after all. But seriously, every user, there's all these different technologies. They all have different requirements, different needs, noise characteristics, testing, even gate types. Users have to be able to plug their own modules in, do their own design and definitions, and then be able to run them in the simulation system. For the compilation, we do multi-level analysis of the circuits. We do lots of optimizations. I'll allude to a few of them in a few slides. We do circuit rewriting. So for instance, you need to rotate something like this, but you only have 3 rotations available. You have to build chains of rotations to get you to the right place. This compiler knows how to do these things. It's, like, for instance, a language where at the bottom level you don't have things that you need. They're very abstract at the top level or very rich at the top level, and you have to compile into a lower set at the bottom. We have noise models, gate sets, and then target architectures. We actually have the physical experiments. We actually have to do things like send pulses, microwave pulses down into the refrigerator that have to be shaped a certain way to make a gate operation happen. You have to do resource allocation. You have to do all the things you're used to doing in terms of you have a target and you have to compile to the target, but now we've got many targets, and they all have to be supported across all of these environments. So let's talk about the actual architecture. We have a top-level language. You're going to see some examples of it, and it's just going to look like F#. The actual simulator is written in F#, and this is a monad inside of F#. Quantum is viewed as a monad or a computation expression. It is easily usable from F# directly. All you see is something to talk to, like a GPU monad, the equivalent. You would talk to it, ask it to do things, ask for things back, but it can't pollute your environment, and you can't pollute its. But it's really just a set of DLLs, so I can put FSI or any other scripting in front of it, and you could use this, say, in a cloud environment, which you want to submit your application as a text script and have it run as a service. You could use C# or any other .NET compatible language that can load the DLLs and talk to it. So you're not stuck in F# if that's not what you want to use. We just prefer it because the functional model actually helps us a lot in terms of our efficiency of code. Everything you write gets compiled into gates. And since this is F#, everything gets compiled into functions. So a gate is a function. That C0 that you saw and all the others are just functions. You call them like any other function. Once you've built this entire system, it gets sent off to a suite of simulators, depending on what you're doing. Currently, we have 3. There's a universal simulator, which will do any quantum operation of any form. Because it's universal, it's limited. We can only do so much on a classical computer. Today, the limit is about 30 qubits on 32 gigabytes of memory. Now, it's all written 64-bit. I can go as big as you want. But 45 qubits takes a petabyte of main memory. It doubles on every qubit you add, right? So a good number is your laptop can do 30 qubits. Hopefully that's enough because you're not going to go much bigger. The biggest computers in the world can't make it into the 40s. So you're probably as close as you're going to get. We have a stabilizer simulator. What this is non-universal. There's a subset of quantum gates that it turns out are efficiently simulable classically. So I can do tens of thousands of qubits in a stabilizer, but I can't do general computation. So why do I want it? All the error correction codes are stabilizer codes. So I can do tens of thousands of qubits trying noise immunity and error correction and work out all of that. I can't actually run any other algorithms with it, but I can design new codes, simulate them, figure out how they work. There's a Hamiltonian simulator, which morally is the same as the universal simulator. It's universal. It'll do everything it does. Same number of qubits, but it's much slower. I mean, I had to come up with some reason I'd write a simulator that was an order of magnitude slower than the one I was actually using. And it turns out it's one of the most useful. Why? Hamiltonians understand time. This is the Schrodinger wave equation that is underneath all of this. It actually simulates the time evolution of that gate being operated. So instead of you do a NOT gate and everything flips, you watch everything evolving over time, and you can do multiple things at the same time while this thing is operating. This lets you do chemistry. This lets you do physics modeling, materials modeling. analog computing, all sorts of things that are possible here in the actual Hamiltonian equation, which is what's simulated or what is described by Schrodinger's wave equation of how this whole system evolves over time. Then you send this off to a runtime. We currently have 3 different classes of runtimes. We have a client runtime, which is your workstation or your laptop. We have a service, which is a well-designed virus. You put it on your network. You say, here are all the machines on my LAN that I have accounts on, and it'll propagate itself out as a Windows service on all of them. Then you can run. You have an ad hoc cluster. You run across your hundreds of machines in your lab, and then it takes itself down and disappears, and nobody knows you were there. I wanted this, so I wrote it. On the other hand, we have the official version, which is the cloud version, which runs on your HPC cluster, runs in Azure. We have this up and running as a service. You can use it in many different ways. But all of this assumed you compiled the code into functions and then compiled and ran the functions directly. There's another whole path. You take these functions and you reflect them back out. So now that you've done reflection, you build a data structure that represents what you're doing in this circuitry, in these gates that are running. Well, now it's a data structure. I can do anything. It's not compiled code anymore. I can actually sit there and play with it all I want. I can optimize it. I can speed it up. I can rewrite it. I can do quantum error correction and rewrite the whole circuit with error correction circuitry in it. I can do rewrites for these primitive gates, or the ones I really have, and I wrote them in more advanced gates. How do I get to them? I can do very sophisticated noise modeling. I can also export it. It's a data structure. And we have 2 typical backends. Classical, say someone at the national labs wants to use a supercomputer to simulate this. We can then generate the linear algebra that would go and run on the supercomputers. Or we have experimentalists and want to run actual quantum hardware. We can compile down to it. And then let's not forget rendering, automatic drawing of the circuits, being able to look at what we've got. If you're interested, by the way, at the end, I'll have a reference to all the papers, so you don't have to copy things down. But there's a paper that's out on the archive which describes the simulator in detail, the language in detail, and for this audience, this is probably the best of the papers I'm going to reference today. So let's do, everyone has a hello world, but we're going to do the quantum equivalent, which looks a little different than the normal hello world. We're going to start with 2 qubits. Alice has 2 qubits. She's going to, again, circuits apply from left to right. We're starting at 0, the north pole on both qubits. Hadamard gate will take that qubit and flip it onto its side, so it's at the 50-50 point on the equator. Then we're going to entangle the 2 together. So we've got these 2 guys together in 50-50 probability, and they're entangled together. It's called a Bell pair or an EPR pair. Einstein, Polatsky, and Rosen, EPR. So Bob is going to take one of those qubits and go far away. And by far away, it could be the other side of the universe. I don't care how far away he goes. But remember, those 2 qubits are still entangled no matter how far away you go. That's what gets this interesting. Alice is now handed a message. She and Bob did not know the message beforehand. They just have this pair that's separated. Alice is given the message. She entangles it with her half of the pair. And then, depending on which form of quantum physics you believe, instantly, Bob's flips to the state that matches the entanglement with that, or after I measure Alice's and send 2 classical bits across a channel, Bob can apply them to his qubit, and lo and behold, the destination's exactly the source to full fidelity. So he can do infinite amount of information with full precision as far out as you want, instantly the side of the universe. But wait a minute, what about the speed of light? Well, we had to send those 2 classical bits, which is the double lines, for him to know how to manipulate his qubit to get the right answer. You had to send 2 bits of information to get infinite amount of data back. Well, that's not too bad, but you had to send it no faster than the speed of light to get the 2 bits there. Without it, if he measured his, he'd get something out and he had no idea what it meant. So you haven't violated any rules, but when did his qubit flip state? And the typical interpretation is instantly when she did hers. It's not speed of light is the problem in terms of the system changing state, but propagation of information. And in that way, we don't violate anything. So I said it's hello world. This is the simplest thing you can build that's interesting, but it's kind of a bizarre hello world because this is Einstein's spooky action at a distance that we're talking about that he didn't like at all. And it works, at least And actually, no, it works. This has been tested in a physics experiment with kilometers of fiber optic cable, and sure enough, it does exactly what it's supposed to do. Let's look at the user code. Now we're in a languages talk, so let's talk a little bit more. What does it take to build this? Well, that EPR pair, it's an F-sharp function. I let EPR be. The argument is a list of qubits. All of my gates take a list of qubits. And then all gates read off that list however many they need and use. So the Hadamard only needs one qubit, reads it off the head of the list, and applies the Hadamard. The C0 reads 2 qubits and does the controlled NOT gate across the 2 qubits. That's the entire function. That's all the user has to write to get that. Here's the rest of it. We're going to take the tail. We're handing it 3 qubits in this case for all of teleport. We take the last 2. We create an EPR pair, C0 it, Hadamard it, measure it, do a binary controlled X gate off of the second qubit, a binary controlled Z gate off the first qubit after measuring, and it looks pretty normal syntax. The only thing I added was the bang bang is just a helper function that says if you've got a list, here are the indices of the elements in the list I want, pull them out, make a new list. So I pulled off qubit 0 and 2 and then passed it in. Yes?
Sorry, you said Hadamard?
Yes.
What was
that? A Hadamard is a type of gate. So an X gate is a NOT that flips it. A Z gate, so X flips around the X axis. That's how the Z flip. There's also a Y and a Z that flip the other axes. Hadamard says flip the Z to a 50-50 position halfway in between. So that was the only special gate in here. In fact, that's the one that creates superposition, and C0 creates entanglement. And those are the 2 that are kind of the basis of everything else used throughout the systems. Okay? And by the way, we can get prettier diagrams. These diagrams are automatically generated. The ones you're seeing are the SVG HTML version. You can also get LaTeX out directly. So for our researchers who are doing lots and lots of publications, nobody has to draw a circuit anymore, which they are very thankful of. But this is just normal code now that we have this teleport function. So we can create just straight F-sharp code that creates qubits, initializes them to some state, prints it out, then call teleport, which does the quantum simulation, then print it back out. And you never knew you called the simulator, you just called the function. And in this case, we have a bunch of random states where there's a qubit that has some complex number times the 0, another complex number times the 1, where the magnitude squared is 1. We run it through the whole system. We read out the outputs, the same number. And by the way, we had to apply the X, didn't apply the 0 in that case, had to apply the X, had to apply the Z in this, and so forth. So given we apply the right classical information we were told across the message space, we get the answers back out. It works. And again, this is the least you have to do, at least prove you can make hello world work. These gates I'm talking about, though, aren't built in. They're just in the library. You can make your own. You can replace them. You can add them any way you want. It's just a data structure where there are lots of optional fields. I've shown a few of them, like the name, maybe a help string, the actual definition of the matrix that it's going to operate, and drawing instructions done in a LaTeX format that says, here's how I'm going to draw my gate. And so you actually can even change the output to look like anything you like. Should also mention, by the way, that a gate is, these are as a normal gate at the bottom. You can also do metagates, so you can build bigger and bigger circuitry as a gate. You could also have gates that are like measurement gates, input gates, reset gates. So there's a whole several different classes of gates. I'm going to do another simple example, just show how a little bit of code can generate a lot of quantum circuitry very quickly. We're going to do that Hadamard again. We're going to take a qubit, and we're going to flip it to 50-50. And then I'm going to remember him. He's the head of the list. And I'm going to take for everyone in the tail, entangle him with everybody, however many qubits you gave me. So now this is a variable length function. You can take however many qubits in you want. And he just entangles everybody with the first qubit. And when he's all done entangling, he's going to take a measurement gate. And the bow tie is a mapping function. It says just apply M to each element in the list. And you could have just said for each element in the list, apply an M, just shorthand. This is what you get. So you've got the Hadamard, you've got all the entanglement, and all the measurements. Well, since they're entangled, I said you can't make an independent copy. When I measure any one of those qubits, I'll get a 0 or 1, 50-50 probability. But once I get that 0 or 1, all the others collapse to 0 or 1. Because they're all entangled together. And so if you look at the output, it's random whether I get a 0 or a 1, but they all measure the same. And this is why they're not independent. I can't just read one without affecting all the others. So now let's move over to Shor's algorithm. This was the cryptography example that everybody knows and loves. This is a 4-bit example, takes about 8,200 gates. Typically, this is factoring the number 15, which is, by the way, about as big as any. I've seen one paper that factored 21, or at least talked about it. But that's about as big as they've ever gone. So yes, this is not something you can't do in your head. But the algorithm scales, if you look at the bottom, 2n plus 3 qubits. So if I have RSA with a 1024-bit key, 2 times 1024 plus 3 is the number of qubits I need to break that. So the actual number of qubits isn't massive. It's in the thousands. It's in the same order of magnitude as the bit key. The amount of time it takes to run on a quantum computer isn't bad. Classical computer to simulate this is terrible. I'll show you how terrible it is in a minute. But you'll also see that we're not seeing 8,200 gates. We're seeing an overview. Since you've designed hierarchies of these gates going up, you can now tell the system render at different levels of abstraction. So these are modular multipliers that are coming through saying, I do all the modular multiplication at this point, then I do these gates, then I do this, then I do this. So you can get different levels of abstraction. Yeah?
Can you model recursion?
Yes. The problem in this simulator is everything has to be unrolled. At the very end, I'm going to talk about what we don't unroll. And so we'll talk about recursion and true looping and all the rest of that. This is pure circuitry, though. This one lays everything out. I should mention that even though in the literature you can only see up to about the number 15 or 21 factored, we factored the number 8193 using LIQUi. That was 500,000 gates. It took 30 days on my desktop. And no one's ever gotten anywhere close to that. So it just gives you an idea of the scale of the simulator. The simulator is about 30,000 lines of code at this point. So let me dive down just into one section of Shor's algorithm, showing you the modular adder, show you why it's hard to write code for this type of environment. The code itself looks fairly straightforward. We're going to create an operator, which is this modular adder. He's going to do a controlled add. So each of the red boxes is each line of F# that goes by. And so we're going to add in the number we want to add. Then we're going to take out the modulo number. We're going to subtract it off to see if we overflowed, right? Just like we do a normal mod. Turns out we're in Fourier space. We're doing this in frequency space. So we're going to invert the Fourier transform to get back into what the bits really are and look if the bit at the top overflowed. So this lets us know, did we really have to do the modular subtraction or not? Now we go back into FFT space, and we use that bit to control whether or not we actually take that n back off or not. So this did the modular add. Normally, you'd be done at this point. But I said everything has to be runnable forward and backwards. And at this point, it's random whether or not that bottom bit is a 0 or a 1. Because depending on the computation, it could be either. It's not necessarily going to be what it was when you came in. And so when you get out the other end, you now have a bit in an unknown state. You're not reversible. So now we have to go all the way back through where we take the number back out, we un-FFT it, we clear the top bit if it happened to be set, put it back, put the add back, and now we're done. And now this circuit runs all the way forward, all the way backward. Now, no, this is assembly level we're talking about. This is not how people are going to write this in the end. But I wanted to give you an idea of what's going on underneath to make this sort of thing operational. Here's timings. We're talking about how hard is it to actually do a classical computer simulating a quantum computer that is doing Shor's algorithm. The blue, red, and orange dots on there are the versions of the simulator. We're on version 3 currently. And you'll notice in the original, the 3-year point became 4 months, became 4 days. And actually, the last point in orange is the 30 days to get the last number I just showed you that we did. So we've gotten massive improvements through optimization. This gets back now to the compiler technology and the math library. I should actually mention also the math library under this is written in F#. There is no C code. There is no assembler. This is not MKL or any other library. This is all done in F# top to bottom. And we've learned a lot about the guts of the F# compiler and what it does well and what it does not do very well at all. Word of suggestion, never do a for loop with a 64-bit value. You will be very disappointed. Anyway, I said error was a major problem in terms of the real systems. Everything we're talking about is error-free. We're just running qubits and using them, and they work. But real qubits fall apart. This is called decoherence. We have a user-extensible module that allows circuits to be written automatically. A logical qubit, one of the ones we've been using so far, could be as big, typically, in a lot of these codes, as 1,000 physical qubits needed for every one logical qubit so that we're immune to error. So that gives you an idea. When you see, oh, this only takes 1,000 qubits to do cryptography, no, multiply by another 1,000, go out to 1,000,000 before you actually have enough qubits to run long enough to make this work. Quantum codes are very analogous to classical codes. If you have 3 bits, and I perform an operation on each one of them, and all 3 agree afterwards, and did the same operation on each, we're good. 2 of them agree, fine. You flip the 3rd one and move on, doing majority voter. ECC, a little bit better than that, but you can build codes that are basically figure out, A, how to detect errors, B, how to fix them. And that's what we do. Same thing works on the quantum side. And so you do the operations on all the physical qubits and then fix them up to make the logical qubit correct. And this is a large area of research. There's lots and lots of people working on all sorts of noise model, codes models. How do we actually make this practical? You also may be limited by the geometry of the machine. I can't have every qubit connected to every qubit. We can't do that in a classical machine with even the bits. So let's say I have a 2D layout. So it's a surface that people can only see their nearest neighbors. Well, if that's the case, we wind up with this sheet and it becomes a surface code. So now you have a type of code that has to be able to operate in a 2-dimensional space. So there are all sorts of restrictions like that that make this an interesting area to work on. Here's an example of one code called the Steen 7 code. The bottom 7 lines are the real physical qubits that make up one logical qubit. The top 6 are measuring what's going on there, figuring it out, and then flipping them into the right places depending on what errors happened. And so this whole circuitry is called the syndrome circuit that would be applied after every gate or after every period of time that you want to look at every logical qubit and make sure the physical qubits making it up are still coding the correct thing. So these are the types of correcting codes. So remember our little teleport circuit, a hello world? This is what it looks like when I apply the Steen 7 code. We went to 27 qubits instead of 3, and it started getting very, very dense. And this is only a 7-to-1 blow up. In some of the codes I'm talking about, it's 1,000-to-1 blow up typically needed. The other problem with noise is it's very hard to characterize. And every one of these technologies has different noise models. So we've built a user-extensible class that lets you come in and say, for these gates, this is the type of noise model. And the noise model, surprise, is a function. You come in with your own outside of the system function that says, here's how I'm going to operate. And what's nice here is you can do things like correlated noise across qubits. System doesn't know anything about it, but you're above it. You can look at them all. OK. I will move things along. So just to give you an idea, this is a circuit going idle, 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 idle. Nothing's happening except noise. And you can see over time, qubits that have 1 values are going towards 0. Eventually, there's a non-unitary event where something decohered. A qubit fell apart. He went to 0. Others went up with higher probability. Eventually, you're only going to measure a 0. There's nothing else you can measure. This is our friend Teleport running with that Steen 7 code on it, showing that we can actually hold off before it falls apart, depending on what our noise levels are. So we can start doing very advanced noise modeling. If I'm that far in, I'm going to have to just skip through the rest of this. I'm sorry, but I'm going to go quickly. I'll be available to talk. The Hamiltonian that's shown in the upper right is what the D-Wave machine does. This is called the spin glass model. This lets you do machine learning. This lets you do optimization problems. It's an interesting way to encode all of this. We can reproduce all the published results. I show what circuitry looks like for doing a simple chain. Let's get into some more interesting things here. By the way, there are 2 papers. People want to know about D-Wave. This is the company in Vancouver that ships a quantum computer that Lockheed and Google bought for NASA. Lockheed bought their own, I should say. There are 2 papers we did. The one on the left is is it quantum or not? And we went out and played on that machine, did our own simulations, did over 1 million CPU hours at MSR, simulating the machine as well as running on it. The other one is, OK, it's quantum. First one did come up with, yes, it's quantum. The second is it useful? And it's all about benchmarking. People in physics and math don't know anything that we take for granted, which is benchmarking. And how do you figure out what is a benchmark? Well, classical machines, we know a lot about benchmarking. Quantum machines, not so much. And this is the first paper that actually says, here's how to unify the two so you can compare them against each other. No details on this, but to show how you could just take PageRank. Take the Google matrix, turn it into a Hamiltonian, turn the Hamiltonian into a unitary, run it through, simulate it with this Hamiltonian, and at the end, here's a PageRank of, this was just 256 pages, but in the blue is the classical PageRank, in the orange is the quantum PageRank. There's a problem with this, though. When you translate, doing it naively doesn't work well. You have to load all the data. We have to do that anyway in a classical system. But once you've loaded it, you have to process it. Well, that's exponentially faster. That's great. That works fine. But now I get to read out these qubits, and I get 1 bit per qubit, and it's probabilistic. So what would happen if I ran PageRank through, I'd get 1 page would pop out saying, you landed on this page. Now load the whole web again, run it really fast, and I'll give you another page I landed on. So it takes you an exponential amount of time to actually load the data. The computing is cheap. And so now you're worse than if you had just ran it classically to start with. That sounds like a non-starter. You're dead. Well, you don't ask the question that way. I'm not going to do the details. There's references, and Mads has copies of all of this. But this paper shows how to do linear algebra, solving linear algebra. So you have an AX equals B. It inverts A and tells you what the coefficients are. The problem is you can't read the coefficients except taking an exponential length of time to read them. So what's the point? Well, you don't ask that question. You solve it, and then you ask the model a question. So for instance, you model fluid dynamics where you're saying, I'm sending a radar signal out into space, or into air, and there's a stealth fighter up there. Model that. And now I'm going to send the signal, and you tell me what the radar cross-section is, 1 number. And I can't do it classically, but I can do it quantumly. So it's not so much what, and by the way, this also tells you we're not supplanting classical machines. This is different classes of problems. But there are some real big money problems that you want to solve that you can't do classically, but you have to ask the question right to be able to do it quantumly. And that was the point of that. You get true exponential speed up. We're working on it. We have it up and running. Great. My first love at the moment, quantum chemistry. So I'm going to zoom through it, but just give you a quick idea. Just say you need very few qubits to do very interesting molecules. We'll just leave it at that for now. That happens to be the Hamiltonian for it. These are some of the molecules we've simulated in LIQUi. I can do real molecules and run them. We have 2 papers out currently. The first one is, how hard is the problem really? This is the one everyone said, this is the killer app. Well, we looked at it and said, you're going to see in the next bullet I pop up why this isn't the killer app. This is terribly slow. It's very few qubits, but the amount of execution is billions of operations. The second one is, well, yeah, but we can do better. And actually, there's a third paper about to come in a few weeks that does even better. How much better? Well, let's look at a molecule called ferredoxin, Fe2S2. Why do I care? It's the center of photosynthesis. It's the energy transport in your body. We can never simulate this classically. This is something chemists want to do desperately. They can't do it. That first paper said at current qubit speeds, 300 million. Now, it's not infinite, though. I mean, classically, you'll never get it older than the length of the universe. Then 300 million actually isn't that long comparatively. But I don't want, this is not deep thought we're building here. Okay, we don't want to wait that long. Second paper got it down to 30 years. So 10 to the 7th reduction. That's not too bad. However, the new paper about to come out, 300 seconds.
Ouch.
Yeah. Proud of this one. And it turns out the third paper is mostly about better error bounds. I didn't change the algorithm at all, didn't change the implementation. It's just the theorists are predicting the wrong numbers, tighter error bounds. And we're able, through simulation with LIQUi, to show they were wrong, and then having them go back and say, oh, yeah, we forgot this. Oh, right, we could do this. And I have a whole separate talk on this. Last one, in the same vein, there are things that are easier to simulate than chemical molecules. For instance, materials, because they're in a fixed structure. They're in a lattice. Since they have only nearest neighbor communication with each other across the lattice, you can simulate them extremely efficiently on a quantum machine. Classical machine can do about 20 little plaquettes. We can do however many qubits you have. That's how many we can do. And for instance, you want a high temperature superconductor. This is how you simulate it. And this just shows, yes, we simulate it, we get exactly what the theorists say you ought to get. Okay, last piece. I got to do one language piece at the end, okay? V2, and back to loops and unrolling. So this happens to be the working code in V2, which is not done yet, that does a quantum Fourier transform. The bold items are the quantum operations. Everything else is typical, what you'd expect. But now we don't compile to a data structure or function. We compile into an AST. We get this AST, and at that point, we can create a rolled AST we start with, an unrolled AST, a circuit for V1. We do all sorts of annotations. We actually have machine models that are nested all the way down. So you can say quantum error correction is a machine model, the physical layout of the qubits is a machine model, time, noise. And then the AST gets annotated all the way down and all the way back up. So if I do a C0, that one operation may become 1,000 things in the AST of, oh, here's resource allocation and layout and positioning and timing. What this lets us do, and by we do the nested symbol tables and generated variables for loops and all the things you do, I've got basically a multi-compiler team going on here doing this stuff. I can now say adjoint of QFT op. And what that does is say reverse this. But instead of just saying run the circuit backwards, this takes that code in the AST, reverses the code, inverts the loops, inverts the quantum operations, and gives you back something just as tight at the end. Looks just like this, but it's the reverse operation. So I want an inverse Fourier transform, I just ask for it. You need to do this a lot, and it's extremely efficient. Last piece, last slide. Stupid things you don't think of when you invent new things. How do you draw this? We now have integrated classical and quantum code. Here's two choices. I've got quantum code that I measure, then classically look at it, decide if I'm done yet, go back and do it again, then finally pass it along. Should it look like that or look like this? Where I have a classical layer, he calls into a quantum box, the box returns, we either return back up and continue, or we continue, and on and on and on. There is no standard for any of this in any field, let alone, there's like 6 that interact here at this point. We're trying to figure out the right ways to visualize this, how to pull it together, how to make it work well, and I'm going to stop there. If you go to the archive, you can either type this in or just look for Wecker_D for all the papers that I touched on through the talk. Thank you.